All right, folks, so here they are, our projectile motion equations in all their radiants. Projectile motion. And as a first example of projectile motion as two-dimensional motion in a gravitational field, we're going to talk about somebody taking a ball and throwing it really hard and throwing it horizontally. Actually, I should say horizontally. So when the ball leaves, say, the pitcher, we're going to have a 100-mile-per-hour ball, which is very fast. Only like major league pitchers can throw a ball that fast. So the ball is going to be thrown horizontally. This is our initial velocity vector. And remember, vectors can move around. It doesn't matter where I put the tail of it. Okay, I'm putting it at height, though, because it's being thrown at an elevation of 1.5 meters. That's how high. So 1.5 meters above the ground. So here's a meter. All right. 1.5 meters is about here, about just below shoulder height for me. Okay, so that's about right. So 1.5 meters above the ground, big league pitcher is going to throw a fastball 100 miles per hour, which is 44.7 meters per second. And notice that what I say here is zero launch angle. What that means, we'll see more later what exactly that means, but what it means is that when the ball or the projectile is launched, it is moving horizontally. Now, it won't keep moving horizontally. You've noticed that if you throw a ball horizontally, right, or again I should say horizontally, it will fall. So if we sort of track this ball, it's going to take on a trajectory is actually the physics term for this, a trajectory through space. It's not an easy word to say either, by the way, especially when you're in front of a camera or lots of people. It's going to take a path something like this. It's going to immediately start to fall and land out here somewhere. Okay? So 100 mile per hour fastball to the right in the positive x direction. This is V naught. Right? But V naught, notice there's no subscript on that. That's the initial velocity. It happens to all be, in this case, V naught x. The initial velocity, V naught, is all in the x direction. This pink vector here has it is at right angles to the y axis. It is pointing directly horizontally. It has no y component at all. The initial velocity is all in the x direction. What is V naught y in this case? What is the value of V naught y? The initial velocity's y component. Is there a y component to that vector? That's the V naught. That's V naught right there. There is no component to it. So V naught y is 0, which means all the V naught y's you see over here, that one and that one and that one, these three, there, and there, all 0, because the initial velocity is completely in the x direction. Love myself some zeros. Makes things simple. Okay. What else is 0? Well, x naught is 0. Right? Because the initial position of the ball is going to be at the x equals 0. We also know what y naught is. Y naught is 1.5 meters. So everywhere you see an x naught here, actually that's the only x naught in the whole set of equations, that's going to be 0. And y naught here is going to be 1.5. Okay. What we want, so that's the situation. That's the setup. What we want to know is, using these equations in this picture with this situation here, is this. We want to know what time it lands. We want to know the position at which it lands. And we also want to know what the final velocity is equal to. Okay? I hope we'll have time to finish the final velocity. We'll see how it goes. Okay? I think we will. So let's just take the first one first. I think I do time first. Yes, I do time first. So, time. Of all these equations, I should say before we start, these two equations, this one here and this one here, are typically not that useful. Okay, sometimes they are, but typically we're usually only going to be using 4 of these equations. Okay, those 2 with stars they're sort of asterisks, they're like also rans. Sometimes they're helpful, but you can pretty much do any problem without using them explicitly. Okay, so we want to know what time is. Let's look at our equations here and find out which one of them involves time and stuff that we know. Well, none of these, right? Because we don't know what x, right? 1 and 3 up here in the x direction, they're not that useful. Here, we don't know x, so we can't use this one. Number 1 in the y direction, let's see, we don't know Vy, we don't know the final velocity in the y direction. We know the initial velocity in the y direction, but we don't know the time, or so we can't use that. How about this one? Do we know y? Yes, y is 0. I didn't mention that, but y, the final y value is 0, right? Because at the end, we're here. The ball's at the ground, which is y equals 0. So we know y. We know y naught. We know v naught y. And we know g. So this is the one to use right here. By the way, number 3 doesn't work either because, again, we need to know v sub y, the final y velocity, in order to find time. Actually, time doesn't even show up in that one, so we couldn't use that one. Okay, so number 2 is the one to use. So let's write it down here and see what we can come up with. So y naught plus v naught y t minus 1/2 g t squared. Okay, let's see, what is 0? Let's see, y is equal to, the final y value is equal to 0. Y naught we know. V naught y is equal to 0. So we're left with 0 equals y naught minus 1/2 g t squared. And we know y naught, it's 1.5. We know g, it's 9.81, right? That's the acceleration, right? We know g. So we can rearrange this for time, okay? So if we add 1/2 gt squared to both sides, we'll have 1/2 gt squared equals y naught. I'm doing my algebra again, okay? If we solve this for t squared will be equal to 2 y naught over g. So t is the square root of 2 y naught over g. Of course, many of you will choose to simply plug in your values right here and solve it for time, which is fine. Like I've said many times, if you want to, at this point, when you know everything but the thing you're looking for, you can plug in your values there if you want to. I just do it this way. So I'm going to stop saying that every time and just do it. So we can plug our numbers in now. 2 times y naught, which is 1.5 meters, over 9.81 meters per second squared. You do your math, plug in your numbers, turn your crank, and you get 0.553 seconds. So time is 0.533 seconds. Takes about a half second, a little longer than a half second for that ball to hit the ground. Okay, now we need to know x. That was the next, so that one is done. Boom, we got time. Now we need to know x. Well, there's only one x anywhere in these formulas. There's only one x anywhere, and that is right here. So we have to use that one. There's no other way to find x, friends, other than to use this one. That's it. So x is x naught plus v naught xt. X naught is 0, my favorite number. So it's just v naught x times t, which we now know. That's going to be 44.7 meters per second, right? Because v naught x is the whole initial velocity times 0.533 seconds, which gives us a answer of 24.7 meters. So that is this distance, right? That's how far the ball travels horizontally before it hits the ground. Okay? 24.7 meters. Okay, now finally we want to do the final velocity. I'm going to erase the green I've got on the board, and we're going to look at the final velocity. I may leave some of the details of the calculation to you to do as an exercise for the student. That's what they say in textbooks when they don't want to do it themselves. They'll say, we'll leave it as an exercise for the student to show that whatever. And then you're supposed to go pick up a sheet of paper and scribble on it and confirm that they're right. I might do a little bit of that here because I'm already at 12.5 minutes. Okay, so the final velocity, I want to be clear what I mean by this. When the ball hits the ground, right, the velocity vector is a tangent to this curve, which means that the velocity vector points in the direction the ball is going. So right when the ball hits the ground, it's going in this direction. Right, it will bounce back up and its velocity vector will change. But when it hits the ground, its velocity vector looks like this. And this is its final velocity vector, and that's what we're looking for. And it's a vector, so we want both the magnitude and the direction. Okay? Of this vector. And we extend the x-axis a little bit here. So just like the eagle, okay, coming down, it had a velocity vector down and to the right. Well, so does the ball when it hits the ground. It's got an x part here. It's got a y part here. And this Vx is that Vx. That Vy is that Vy and that Vy. And that's what we're looking for. We want to know what the final velocity vector is. So to find that, we've got to find, the only way to do it is to find Vx and Vy separately. Okay, what does Vx equal? It equals V naught x. Okay, that formula is useful here, but if you remember that the acceleration in the x direction is 0, you don't need to do any thinking about what the velocity is in the x direction. If there's no acceleration in the x direction, then the x velocity does not change. The x part of the velocity does not change. So the x part of the velocity is exactly 44.7 meters per second. There's no acceleration left to right. All the acceleration on this ball, and this is a little hard to wrap your head around, is down. So if the ball was right here, the acceleration on that ball is down. There's nothing accelerating it to the right. This acceleration in the x direction is 0. So its velocity, if its x velocity started at 44.7, it'll always be 44.7. Okay. Now, you can prove yourselves that Vy, and this is the the exercise I'll leave for the student, is minus 5.2, minus 5.42 meters per second. So this part here is minus 5.42 pointing down. So the final velocity vector is 44.7x, sorry, meters per second. Meters per second in the x direction, minus 5.42 meters per second in the y direction, using our unit vector notation. It is 44.7 in the x and negative 5.42 in the y. Okay. You can also convince yourselves, using your vector skills developed last week, that this is the same as 45.0 meters per second at negative 6.91 degrees. So this angle here is theta is minus 6.91 degrees. Okay, we are over again at 17 minutes. Okay? Review it, become it, ask questions. Don't be shy.